Did you guys just have a test or something? Or nothing?
We're never this happy after.
Huh?
We're never this happy after.
Yeah.
What?
Like it's so loud.
Because everyone knows the transit blows up. It's your fault.
All right. First, the quiz. There's the solutions are up for the quiz. Let me just tell you before I start talking about this. There were basically a whole lot of ways to do this. You could do it by either doing the flux coupling, find the flux through one link, either by using a magnetic circuit, or by saying, you know, you had Ni current going up, and therefore the H field would be just Ni over 2 pi rho, multiply that by mu naught, and you found, and I'm going to go through this one. Multiply that by mu naught, and you have the B field. Integrate that over the surface. And that's the flux through one turn, and multiply by N. That's the flux through N turns. Divide that by I, and you get the actual inductance. Second way to do that was basically find the energy. You did it that way, but you messed up an integration. But the fact is, only a couple people did it that way. They found the H field, then they took that, squared it, multiplied by mu naught, and multiplied that by 1/2, and integrated over the volume. And then they set that equal to 1/2 Li squared, and calculated L by dividing that by, multiplied by 2 and dividing by I squared. That's the second way. Third way is just build a magnetic circuit. I did this, I don't know if you realize it, right before I gave you the quiz on the board for one reason. So everybody saw how a magnetic circuit could be used to easily solve it. Y'all follow me? Now, magnetic circuit gave you an approximate value, wasn't exact. But what I try to do is give you as many options as possible to do that. You didn't have to do it alone. Who told me that? Somebody told me that we had too many choices or something like this to do it. Did you do that, kid? No. Somebody, oh, who said? You said it. Yeah, beautiful. Anyway, I didn't try to confuse you. I feel bad that some people, I got all these little notes that we studied cylinders. Yeah. It is cylindrical if you think about it, right? So it would work, but they don't just try to study a very small class of problems. Try to understand the concepts. Because if you don't, what happens, especially on a final? You're looking for problems that look like this, and they don't look like that, so all of a sudden you don't know what to do. But if you understand the concepts, the physics and stuff like this, you can solve any of these things. Y'all with me? Now I'm going to do this one with the magnetic circuit approach. You have your quizzes. I'm just doing it because I really felt that it wasn't meant to be difficult. It was right out of what I had on the board. There were several homework problems related to this, and I felt bad that I didn't somehow hold you accountable to this in the homework or something. So I'm going to go through it real quick, okay? All right, for this thing, you basically have something with a rectangular cross section. You got an inner radius, I think A, outer radius B, and height C, if I'm not mistaken. Correct, class? And this thing's really this way. I'm never going to be able to draw this well, but what I'm trying to show you, there's a circular, the thing looks like a donut basically, a square or a rectangular cross-section donut. And here we have N turns on the thing, so I'm just going to show you a few basically coming like this. But we have, and you got it there, we have N turns. Sorry, N turns. And with that in mind, so I'm asking for the inductance. The way you always do the inductance, if you're going to do a magnetic circuit, you get I, and from basically Ni, that's going to be your voltage source, or your equivalent MMF. So the MMF would be equal to Ni. We have that, right? Now the next thing you need is the equivalent magnetic reluctance. This is where the approximation comes in. So I need the reluctance, magnetic reluctance. And you know, in general, it's proportional length. Now this one, because of the radial distances, that the width of this is actually, I believe, 1 centimeter, and the height of this is 1 centimeter, and the inner radius is 2 centimeters. There was an approximation in this one. Typically, I would make this like 20, 30 centimeters would be the first radius you counted, and then 21 centimeters. That way, the B field is just about continuous across the cross section. Y'all with me, class? So I'm going to do it this way. I'm going to find the length by taking the actual average length around there, which would be using the radius that is really the sum of A plus B over 2. So I'm just going to call this, I'll call it RW here, or R, call it R average. And that's going to be B plus A over 2, and that's 2.5 centimeters. You know what? Yeah, 2.5 centimeters. Now after that, I get the B field. All right, and after I have that, now I'll use that general formula for magnetic reluctance. It's equal to the length, its constant cross-sectional area, so A, and then divided by mu. Does everybody understand what I'm doing here? Give me a show of hands if you do. This is the general form, is it not, class? The length would be 2 pi times the radial distance that I put up there, the average radius. Y'all with me? And if you, I gave people a lot of leeway. If you use the inner or outer radius for this, I gave you full credit. And if I didn't, come see me. So for this one, I find the magnetic reluctance here equal to L, which is going to be 2 pi times that RA. It's just the average distance between the two. Over A, and A is really going to be the width times the height, or it's going to, I'll just put A here, but A in this one is equal to 1 cm squared, and that's really 10 to the minus 4th meters squared, and that's divided by mu, and mu is just mu naught. Y'all with me, class? Everybody see this? Just how many understand what I'm doing? This is the problem I did on the board just before you took it. I tried to. So this is, we've got this, and this is just 2 pi RA. RA, that's divided by cross-sectional area mu naught. Now the next thing is we get the magnetic flux. Magnetic flux is going to be the MMF divided by the magnetic reluctance, or it's equal to simply Ni right here, divided by 2 pi in radius, and I might as well bring the A and mu naught up top. Can everybody follow me why I'm doing what I'm doing? Give me a show of hands if you can. Y'all with me? Now, that's the flux, but that's the flux through one term. Y'all with me, class? We have to find the flux linking each term, so you multiply this by n. That means the total flux, or the flux linkage here, is going to be equal to n times the magnetic flux there, or it's n, and there's another n here, so it's n squared IA mu 0 over 2 pi RA. Y'all with me? And the last step to get the inductance is just divide out the current that you assume. Y'all with me? What I do a lot of times, I assume the current's 1A. That way, at the end of the day, I don't have to do anything. It doesn't matter what the value of current is. So now you divide by current and you find the inductance, and this is an approximate value. It's going to be equal to n squared times A times mu 0 over 2 pi RA, and that's approximate. I think that was slightly high. Can you all see the solutions on OneNote, class? I don't remember what the value for that is off the top of my head, but the method's important. Y'all with me? And it's usually easier to use a magnetic circuit to calculate inductance than going through like the energy definition and then doing the total integral and setting it equal to 1/2 Li squared, or just integrating the magnetic field through one term, and then if you have that, multiplying that by n to get the flux linkage. But in either case, you'll get approximately the same answer. They're very close. With me? Now, the second way we'll do this is just going to be, we're getting the H field in here and then doing the integration. You get a natural log when you're done with that. Okay. Any questions about this before I move on? All right. Now, magnetic circuits are important. You're going to get them in power. How many have had magnetic circuits before in power or some other class? You've had in what class? Power. Anybody else? What's that? Who did? You omitted it? All right, well, I didn't. Anyway. No, it's real important. I'll tell you, to understand transformers and stuff, this is the easy way. You can make it hard. Well, I should leave that out there, but I think you know you've got it right before you. So the second way to do this, I'm going to get, well, actually, both methods, other methods, the energy method and the flux method, you have to get the H field. Now, remember, there was a couple of problems. There was a toroid problem, and I've got the other problem. But you remember that what we can do is if we get, if we assume, if we use basically Ampere's law, the integral of H dot dl over the closed loop is the I enclosed by that loop, right? Now, over here, remember what we talked about. If you look right down the z-axis, you got all these terms. I'm just looking at the inside at radius b here. Each one of these in turns has a current that you have to assume I. Can everybody follow me on this? Are you with me, everyone? We have, all right, so when I come out a distance rho away, and I go ahead and I put my closed contour path here, and I'm looking for the H field here. The N, or the value of I enclosed is N times the single current. Y'all follow me? So over here, I get Ni, and then, because it's an assumed dot, then I have to divide, that's going to be really what? It's going to be 2 pi rho H phi. Does everybody understand this? This is basically the same thing as all the current on the z-axis, right? And it's an argument of symmetry used for this, but it works. Then, so now I can get the B field by saying it's equal to mu H, or it's equal to mu, just mu 0 in this case. H is really going to be Ni over 2 pi rho. Over 2 pi rho. It's in the A phi direction. Being a little casual with this, but everybody follow me on this? The units would be what? Webers per meter squared or Tesla. Y'all with me? Now after that, now to get the flux through one turn, we have to integrate that over the surface. This is a more exact answer. Y'all with me, class? So now to get the total magnetic flux through one turn would be a double integral of that, which is going to be mu 0 times N times I over 2 pi rho. It's in the A theta direction. What's the differential unit of surface right here, if you think about this? Well, it's d rho in this direction, isn't it? And this direction is dz. Does everybody follow me on this? Let me see your hands if you do. So it's d rho dz. There's no d phi in this. Y'all with me, class? So it's going to be, it's a phi here, and then it's dotted with d rho dz, but that differential is in the same direction, a phi, because it has to be perpendicular to the actual surface area of the differential. Follow me, class? All right, so the dot product of a phi dot a phi is 1. I'll get rid of that. Now we need the limits. So where does rho go from, class? From A to B. And where does Z go from? 0 to C is fine. 0 to C. So that means the magnetic flux through one turn would be equal to mu 0 n I over 2 pi. Now the dz integral, it just gives you z from 0 to c is c, right? And then when you go ahead and do the d rho integral, you get natural log. Y'all agree with this, class? Natural log from b to c. Or I mean, A to B, pardon. From A to B. That's per one turn, right? Now we have to multiply that by n because there are n turns. I have a comment after that. So when we multiply this by n, I'll just do it here. Now that's the flux coupled through all the turns. Now to get the inductance, just divide that by I. That's the method you always use, it always works. So if you divide that by I, this would be the inductance. That'll give you a slightly different answer. I think that's 6.9 something, or 6.8. Are you looking at the solution online or not? I mean, anybody looking there? They're slightly different. I mean, there's like one is 7, I think, and something, the other is, what's that? What is this? For this one? Or the other one?
Oh, it is.
Magnetic circuit's a little higher. And what's this one? 6.1?
827.
6.827? All right, so the inductance here is 6.827, and that's Henry's. Is that Henry's or no? Oh, it is Henry's? Because how many turns was that? How many turns? 50 or not?
8,000.
8? Okay, that makes sense. So this is Henry's. Now, I got to say something. Remember this. Anytime you're talking about self-inductance and there are turns of wire involved, the inductance is always going to be proportional to n squared. Then it's times the geometric factor. You with me, class, on this one? It'll always be proportional to n squared. If it's mutual inductance and you have a set of turns, then a second set of turns, the mutual inductance is always proportional to the first set of turns, the primary, times the secondary. All right? Y'all hear me on this one? Did you have a question? All right. Now, I'm doing this for a reason, because you're going to see this. I don't know how many different classes you're going to see stuff like this, but you should see it in power, omission or not. You should see that, because he talks about transformers, doesn't he? You've had how many have had transformers? All right, I'm going to go through the transformer thing right now because it's a logical thing to do next. It's not the way the book does. We'll talk about magnetic forces and boundary conditions in a second. By the way, where's that candy? Is it all gone? Oh, there's a bunch. Can you just pass the candy around? Grab it and just pass it. So anybody wants some, grab some, pass it on. And at the end of the day, if there's still anything left, whoever wants it can run away with it, because I don't. Okay, now we're going to talk about transformers. This is in his book, and he doesn't do much on this. Hold on.
I'm just happy that you guys
I don't think I heard that, Russ. I hope I didn't. I know it's in his book. I think it is. Oh, never mind. Let me just show you this. It's scattered through, part of it's in chapter 4, some of it's in chapter 5. But I'm going to talk about just the transformers in a general sense. I'm trying to give you this because we just did coils of wire problems with magnetic circuits. So typically, this is sort of what a transformer is. And you've all had this, I believe. You're going to have something like this, and it's going to have a whole lot of turns here. And there'll be a dot. This is the primary. And you can assume some current I1 going in, and there's a voltage here, V1. And then there's going to be a second set of turns here. And you can assume a current, yes.
From what page?
are you working from in the book?
That's a good question. I'm looking for, I think he does transformers, unfortunately. This circuit's in 294, it's in chapter 5, it's a head. What I'm about to show you, the concept will be the same though. Y'all with me, class? So this is a head, and one other thing about transformers, I haven't gotten to this yet. They rely on time varying currents. They do not work at DC. It's a very important thing. Fundamentally, if you don't have a time varying current, you will not have transformer action. But that comes chapter 5. I'm just showing you the concept. Now, if you think about this, assume this thing has some mu relative, and assume mu relative is much, much greater than 1. Actually, you would have this kind of a cross-sectional view would be like this, and I'm not going to even try to draw all this. Anyway, it'll assume that this, each one of these things from here to here, will have a certain cross-sectional area A, and I'm just showing you this in a general sense, and there will be a total length around the path. So there's going to be some length here, and this is just showing you the simplest possible transformer type problem. Y'all with me? Now, if you look at this problem, the simplest way to do this, if we assume a current I1 there, right? Then what will happen is, if we have, and I'll call this N1 turns on the primary, some of this stuff, let's try this. Let me bounce. Getting better. I'm getting better. I'm going to have to get a bunch of markers. These are always, I think, the COVID markers. They're basically dried out. And let's not do that quite yet. All right, this one. We'll call this N1 turns on the primary. And we're going to have N2 turns here in the secondary. Now, what I'm going to do is say this. I mean, how many have seen this kind of model somewhere? I mean, transform. What class did you get? Circuits or not? Did you get transformers in circuits? Kind of, sort of?
Power.
All right. How many have had power? How many have not had power? Where'd you guys see it? Did you say you saw it in some class? Transformers are very common. A lot of times in high school, if you're taking anything where you have to build something electrically, they'll tell you about it, right? And they're used to step up voltage from either 110 to a much higher voltage, like 10,000 for a neon sign, or they'll take like 7,000 volts, which is one phase of the actual power company's residential power supply that's on the poles. And they use a transformer to step it down to 110. You have an electrical background, don't you? All right, I'm telling you this to give you an idea of where this is applicable. These transformers are used for a lot of things just everywhere. You're not going to get away from them. So if we have this transformer, if you look at the primary, right? I'm going to build a magnetic circuit. If you look at the primary, you're going to have plus to minus Ni, I'll call it N1I, the MMF, and we're assuming an I1 here. Go with me, class? Now, what that's going to do is have to cause a flux. Remember, I don't have anything attached here, so we can assume second current is 0. Y'all follow me? Otherwise, if I had something attached, I would have to calculate the voltage, which we will do in chapter 5, and then divide that by the actual resistance to get the current in the second one, and then show an MMF there, but I'm not going to because I'm assuming it's 0. Y'all with me? Now, when you have that, the actual reluctance, magnetic reluctance here, is proportional length, and I just used L here. Normally, you would get a length from here to here, and a length from here to here. You would have to add them and then multiply by 2 to get the total length, and that assumes the cross-section is the same. Y'all with me, class? Give me a show of hands if you understand what I'm talking about. So the magnetic reluctance would be L, divided by, really, mu relative, mu naught. That would be the permeability inside the transformer. And typically, like for transformers, mu relative is 1,000 or more. And then, after that, the area. And I just used A. So that's magnetic reluctance. So I'm just going to put it down. that means this magnetic flux that flows in the transformer would be equal to Ni, and this is N1, the primary, divided, or it's Ni itself divided by, oh, hold on. Let me do it this way. Yeah, I can actually do it. Just put Ni, I1 over the magnetic reluctance, and I don't have to rewrite that all the time. Are y'all with me? So that's the actual flux through one term, right? Now, what's important with transformer action is not the flux through the primary this time. It's the secondary. And I'm going to say this as N2. So the amount of flux linking the secondary on the second one will be equal to N2 times, and this would be N1, times I1 over the magnetic reluctance. Are you with me, class? How many know how to get the induced voltage at that? Anybody? Current's zero, right? There's no attachment. But how do you get the voltage? Anybody know? This is Michael Faraday's law of induction. We're going to cover that in the upcoming lectures, in the next 2 or 3 lectures. The way you find the induced voltage, the actual voltage induced right here, in magnitude only in this case, this would be the actual measured voltage, would be equal to this. It's the time derivative of the flux coupled in the second coil with respect to time. And that's going to be simply N2, N1 over the magnetic reluctance here. And then it's di1 dt. Now, what I just showed you without saying it, this is, and that is the EMF. Technically, there's a minus sign here, but don't worry about that. This is the mutual inductance between the primary and secondary, that term I just boxed. Y'all follow me? This comes up later. I want to give you a preview. How many have had something like this in your power course wherever? You've had it? Has anybody, have you guys had it? You've had it in what course? Sure. Is it power? You didn't have it in circuits though. When I taught circuits years ago, we had 3 quarters. We didn't have 2 semesters. And we had one where we did do, there was op-amps and transformers in that, ideal op-amps and transformers. I guess they don't teach transformers. Do they teach op-amps in circuits or not? Well, you get op-amps, when I teach signals and systems, I introduce op-amps. I don't know if they do now. And when you get, standard analog electronics, you get op-amps, don't you? What's that?
We get op-amps.
Okay, good. Ideal op-amps or actual op-amps? Ideal is 0. I mean, there's no current in, no voltage across the input. That works to a high, it works well, but at high frequencies especially, you have to use the complete model, and you have leakage current, because the input on an operational amplifier is actually, well, it's a differential. It's got 2 transistors that are in that differential feed mode. Do you all understand what I'm talking about here? You're going to have 2 transistors that's either FET or bipolar, and you feed between the inputs of both, and you get the differential input, and you will get leakage current, and that's important to consider. Yeah.
That N2, N1 over.
This is N2, N1 over the reluctance. The reluctance is not a function of current, but it's times didt. Now, obviously, if you look at that, no time varying current, no voltage. We'll get to why that's the case in a bit, but I wanted to get through this. Now, next thing we had to talk about, I was trying to talk about, was actually magnetic forces, and then we'll do the boundary conditions. Now, did I cover anything with magnetic forces in this class? Nothing? Okay. What's that?
I think one of the homework problems had the force.
All right, but I didn't cover it on the board. We're going to go through it. Magnetic forces are real important. And I'll give you the formula for differential on a charge and on a piece of current. They're the same ideas, but this is important. By the way, where are the candies at right now? Where the bag? Are they all gone or not? Good. Keep passing them around. I'm trying to get rid of them before I... All right, here's the deal with forces. If you have a little chunk of current, I, I'll call it IDL. You'll notice I give it a vector sense. That could be I, DZ, AZ. It has to have both a differential length and a direction. When I have this, and it's in the presence of a B field, just say the B field is homogeneous everywhere. The force on this one will be, the actual differential force is equal to I dl cross the B field. Y'all with me on that? I didn't do this. For some reason, I thought I might have mentioned. Maybe I did. Okay. So that's the differential force. You'll notice two things about this that are important. The differential force is perpendicular to dl, and it's perpendicular to B. Y'all hear me on this? So if I have a B field in this direction, and I have a current in this direction, the force on it is 0. Y'all hear me? With me, class? How many remember this from physics? This is a very, very common thing in physics, right? Now that's with a differential current. If you have a charge, a differential charge Q, moving in a direction V, I mean it has velocity V, velocity has magnitude and direction, and it's in the presence of a B field, the differential force on, actually it's the actual force, if that's an actual charge, the actual magnetic force on that would be equal to QV cross B. And you can see that this is actually a current and this is a current, isn't it? That's a differential current. You all with me, class? You can see charge moving at a given velocity is current. With me? Now that force is always perpendicular. It's real important. Now here's the classic problem that you should appreciate knowing. It may be the one in this book. Suppose I have it, we'll assume it's infinitely long wire with a current I1 in it. And then over here, separated by some distance d, I have a second current. I'm going to put the currents in the same direction, I2. Remember, these are infinitely long, parallel, like railroad tracks. And I want to know the force per meter caused by I1 on I2. So I want the differential force, or I want the force per meter. So if this is 1 meter, what I'm looking for is the force on this. And I'm wondering what it is. So let's go through this based on what I just showed you right here. Now, there's one important fact I kind of omitted. The B field that we're talking about inducing a force on here cannot be a function of this current at that point. Y'all with me, class? So it's a B field caused by a secondary current. Y'all with me? So the B field here is what? Let's put a coordinate system. Let's call this Z going up. And might as well call into the board phi. That means this direction would be rho, right? And phi would be A phi would be into the board. Can you all at least follow my thoughts on this one? I'm trying to make it simple. So we'll assume this one's on the z-axis, I1. Can you all see this? So what's the B field as a function of radial distance? Put it up here. B field would be what? It's proportional to mu, isn't that right? Then it's times h. What's the h field from an infinite wire at a given radius rho? That's right, it's just I over 2 pi rho in the A phi direction. This would be I1. Do you all agree with that? How many see this right here? That's the B field caused by that assumed current on I1. Now, if we do the cross product on this, we have to take a look at what I dl is here, I2 dl. What would that be? Well, it's I2, whatever it is, right? It's going up in that direction, so it would be the differential dl here, because it has to take into account the direction of that current, would be dzaz. You all see that, class? I'm going to do. All right, so I'll write it over here. When I get a look at the differential force, this is acting here. The differential force would be equal to I, EL, which is I2 dZAZ crossed into the B field. And the B field is mu I1 over 2 pi rho A phi. Y'all agree with this? All right, you all agree? So what happens? The differential force on this one would be equal to mu I1, I2 over 2 pi, right, divided by rho and this should be in the rho direction, but I take it back. It's minus rho, minus a rho direction, and this would be times dz. Y'all follow me? I'm going to show you. This is an important point. Everybody agree with this class? We got z cross rho is minus, or z cross phi is minus rho, right? Now, here's an important point. That means if we want it per meter, the force per meter, you'll notice if we integrate this, it's just the dz integral. Rho is a constant, rho would be d. Do y'all see that? So it's just multiplying it by 1 if it's per meter. Do y'all follow me? Let me see your hands if you do so I can tell you. You understand? So that means this force per meter here would be mu I1, I2 over 2 pi. The distance here is d, and it's in the minus a rho direction, or the force is in this direction, not that direction. Y'all follow me? Now, think about this for a second. Both currents, same direction, force would be pulling together, right? What happens when they're in opposite directions? What happens if that current right there was in the opposite direction? Erase all that. So if I had this, and this is I2, not that, what do you think would happen to the force? What about the magnitude? Any difference in the magnitude for a force per meter class? If I1 and I2 are the same, the dimensions, not at all. But what happens to the direction? What? Pushing apart, right? This is an important thing I'm telling you, because if you get very high current lines, you're going to see some of this. You'll see the wires jump. So in a standard mode of driving things, it's called differential mode, you're going to have current in one direction, same with extension cord. Same magnitude, opposite direction current next to it. Y'all with me? Those two tend to push apart. If currents would be common mode currents, same direction, they pull together. Y'all with me on this one? So, as the current gets very large, like kiloamps, you can actually calculate the forces. Kiloamps, maybe even megaamps, we have wires that are in the same direction, they pull together. But if they're in opposite directions, literally, you'll see wires rip apart. Where I saw this most clearly is when we had a rail gun years ago. We don't have that anymore. We would discharge this bank of capacitors. It was at 10,000 volts. I think it was 32 millifarad total, an enormous amount of energy. And we had that, then we discharge it, and we get 20, 30, 40, 50 kiloamp currents. And we had wires that fed into this railgun pretty close to each other. What you'd see is, because they're in opposite directions, one's going in, the wires jumping. As a matter of fact, it started to scare me. Another thing we saw, and this has to do with magnetic forces later on, but we had to make this huge inductor out of PVC pipe, and we wrapped it with 4-amp wire. This is to slow down the rate that the actual current is discharged from the capacitors. If we don't, then we don't fire this thing. It has to be a continuous slower rate. So we had this inductor. We wrapped it. And of course, the students enjoy experimenting with things, so they would throw crushed up aluminum cans in the core. And when we fired, those things basically became a mortar. They would fly into the ceiling and crush the can down to almost nothing. That's called a magnetic pinch effect. Has anybody seen anything like this? I'm sure it's on YouTube, but they didn't get it they didn't record it out of there, at least that I know. Anyway, we saw that. I saw all sorts of magnetic effects, including wires jumping because of this. And I also saw something we'll get into later called induced voltages from a ground loop, and actually arcing out of the wall. Because when you get there's a huge magnetic field. Think about it, 50 kiloamps. Time rate of change is enormous. We would induce voltages unbeknownst to us that would happen. And see arcing sometimes, which scared the heck out of me. So we had to do all sorts of stuff to mitigate that and prevent any serious damage to us or the building or anything in that building. And that was an interesting thing, but it has to do with magnetic force. Now, there's one other thing I'm going to tell you about this before I continue on. When a nuclear weapon goes off, there is an enormous amount of current, they're called Compton electrons, that get thrown out of the center. It's left with this very positive core. You all with me? Now, when that happens, anytime you get charge separated, the parent charge will attract the electrons blown all over heck and try to get back to it. And they get back through the lowest resistance or impedance path. That should make sense to you. So, do you know where these South Pacific Islands tests were? It's called Starfish and Fishbowl. They're in the Bikini Islands. Anybody know this? This is a hydrogen bomb. These are nuclear weapons that are atmospheric. Look, they're 2,000 miles from Hawaii. What could go wrong? You're so far away, right? Problem is, when they go off atmospherically, all these electrons get into the ionosphere. It's a low conduction path, and they want to get back. And the seawater is ideal. And as it's coming back, there's Hawaii with a power grid. And it got on the power grid, like if you know anything about the solar wind and the induced stuff up in Alaska with the pipeline stuff, this is an extreme current, took out the whole power grid. That's one thing I'll tell you about, because all that current got in there, enormous voltages, wires pull together when you get currents of kiloamps, megaamps, who knows what the currents were, destroyed the power grid. Second thing that actually happened, and I can't verify this, so I had a professor that worked on some of the early nuclear testing, and I actually met a guy that was working at the Manhattan Project. That was the initial weapons development. His name was Foote at Penn State. But my professor said that, and I cannot verify this, he said that when they were going through and looking for the assessment, the aftermath of nuclear weapons years later, because what happens is the sand gets fused into quartz, basically. It's so hot. It's, I don't know how hot, 10,000, 100,000, whatever. It fuses it. So they're looking through, and there's, out west, there's a lot of mines, silver mines, things like this. And they're looking, and apparently railroad tracks were fused together. Remember, currents in the same direction, right? Pull together. Do you know how much force it takes to do that? Tons per meter, not pound, tons per meter of force. You know how much current it takes? Megaamps, tens of megaamps to do that. That's how much current was generated by that small atomic weapon that went off in the desert in the tests. Nowadays, that was 100,000 kilotons. Now they got 20 megaton stuff. Whatever happens when those go off, who knows? I just hope I'm never wrong. Yeah.
Is that the idea of EMP?
Now that's a fast transit. EMP is an electromagnetic pulse. It's propagating, and we're going to talk about that later. But it's propagating. It's a very fast waveform, which means electronics especially, it can get through the smallest cracks. It'll pierce through that right when you travel, unless it's hardened, a real hardened thing, you can't. And it gets in there and destroy electronics. It'll destroy transistors. It will not destroy vacuum loops. So this is a little add-on here. Now, I want to do one other thing too with magnetic forces before I move on. I'm telling you that story because sometimes stories like that help you retain information. It's not as boring as. Another thing you can do, based on some of the force things I just showed, you can make a coil gun. Just wrap a whole bunch of coils of wire around some PVC. You know what these cannons our kids used to make with pop cans, they put lighter fluid in, put a dentist on, boom. Anybody do that or not? Some kids are, all right, well, I did it. We did all sorts of stuff when I was a kid. I wouldn't recommend doing it. I don't want to admit to it. But that was cool. Well, these guns are silent. And a coil gun, I actually helped a kid in textile engineering build one of these things for a different purpose. But I didn't realize it was silent. So he discharged this capacitor bank into there, and the nail went flying into the wall. And I didn't hear anything that sounded like a bang at all. Railguns are different. There's a big bang. And it went to the wall, and I'm thinking, this is an assassin's weapon. That comes later. I'll just whet your appetite with that. Back to magnetic forces. You can look it up, coil gun. Anybody ever see a coil gun in here? Nobody? Look it up on YouTube. You can, I mean, kids make those. You can look up railgun and coil gun. A rail gun is two parallel rails. It causes an enormous magnetic field that is used to send a projectiles between them down the thing. I'll talk about that later. All right, a coil gun has a ton of coils, the induced magnetic field. The currents never touched the actual object. It's the induced field effect. That's pretty cool. Look it up if you want. You can they probably have plans to make these things. I hope the guy knows what he's talking about. And I'll kill your son. All right, I'm just about out of time. Let me just tell you what I'm going to do. Now, you all know what torque is, class? All right, let me just finish this up. So if you look at torque, this is a symbol for torque. It's in foot-pounds or Newton meters, depending if it's English or if it's SI units. So torque is always going to be what? It's a radial distance, a vector crossed into a force, isn't it? Remember this class from physics? Let me tell you where it is in the book, and I'm not going to have any time, I don't think, to do this right now, but I just wanted to give you a heads up. This is where we're going. So if you look at torque, I promise you I'll do boundary conditions next time, but this is on page 246, and this is standard. Have you all had statics, right? Torque, all right? All right, some of the moments is zero, some of the forces is zero in static problems. In dynamic problems, it's a little different, but, so that's torque. And I guess I'm out of time. I'll pick it up next time. I'm getting that look from everybody. I'm going to postpone the quiz on Friday. I want to cover some new material. I want to make sure that we're clear on magnetic circuits. Catch up on all the magnetic circuit problems, please, if you haven't done it. I'm going to cover the torque boundary conditions for sure, and then we'll be moving into chapter 5. Now, I need everybody to be on the same page here, because some of it gets very confusing if you're not when you get into chapter 5.